Hi, this is Professor Fernandez, and this is video 1 in lesson 14. We're talking here about the local extrema portion of the theory of optimization. We'll talk about that in the context of this example from Calculus Simplified. So we are going to be using a few concepts here that are going to be important, like critical points and to some extent the increasing decreasing test to solve this example. I covered those concepts in a previous video. This is video 13.5. So take a look at that if you'd like a review of that. I'm going to assume that you're reasonably comfortable with these notions and to just kind of use them in this example. There is one new thing that I will use. That's the first derivative test. That's down here. So let me just zoom in here and tell you very quickly what this first derivative test says. So this is one of the first ways to determine whether a given critical point is a local maximum or a local minimum, or just local extremum in general. What does it say? So it says, suppose f is a function and c is a critical number of f. Critical number. So by that I mean that x equals c is a critical number of f if either f prime of c is 0. You might have also known these numbers as stationary numbers, or if f prime of c does not exist. Okay, so that's what makes x equals c a critical number. All right, so suppose you have a function and c is a critical number, then you apply one of these options, if you will. You look at the first derivative and you see if it changes sign. If it does so from positive to negative as we cross x equals c, then the function has a local maximum. Okay, so here's what that would look like. Here's the first derivative. Here's c. If it goes from positive to negative, that implies local maximum. If the first derivative goes from negative to positive as we cross x equals c, then that is a local minimum. Okay, maybe I'll put my m's look similar here, so I'll add some detail here. This is part b, by the way, local minimum. And if the first derivative does not change sign, either you have this or you have this, right? Then you have no conclusion. There is no local extremum at c. You have no conclusion about the local extremum in the sense that it's not a maximum, it's not a minimum. There is no local extremum at c. So those are the three options for the three conclusions that you get from the first derivative test. And then let me show you then how to apply them for this example. So what does it say? Find the local extrema of this function. Great. So there's kind of a process for doing this, right? Because we're going to use the first derivative test, we need to find the derivative and then the critical numbers. This is a polynomial, so we differentiate it using the power rule applied multiple times, 2 times here. The derivative of x to the fourth is 4x cubed. The derivative of x cubed is 3x squared. Okay, so that gives us in factored form, right? I can pull out a 4 from here, and I can also pull out an x squared from both of these. And what am I left with? From this term, I'm left with just x. And over here, if I pull out a 4 from 8, I'm left with 2. Multiply the 3, I get 6. So x minus 6. Great, this is my derivative. And now I'm going to find my critical numbers. So I'm going to do two things with this derivative. I'm going to set it equal to 0, and I'm going to ask, are there any x values where this derivative does not exist? That's usually the easier question to answer, so we'll answer that first. This is a polynomial. There are never any x values where a polynomial is not defined, right? The polynomial has no vertical asymptotes, has no, crazy oscillations or something. I don't know. There's nothing going wrong. So no, there are no critical numbers contributed from that part. So I'm just now going to focus on setting 4x squared times x minus 6 equal to 0 to find those critical numbers. So this gives me 4x squared equals 0, gives me x equals 0. And then x minus 6 equals 0 gives me x equals 6. So these are my two critical numbers. So when I set up my sign chart, right, I want to set up this over here for this problem. I'm going to look at my derivative, and then I'm going to put 0 here, and I'm also going to put 6. And the whole idea in the first derivative test now is that we are going to choose x values that are in between these critical numbers that we got. And then insert them, substitute them into the derivative, and we're looking for positive, negative, and then at the end, when we fill out the sign chart, we will look and step back, See if it looks like this, local max. See if it looks like that, local min. Or if it looks like one of these two other ones, no local extrema at x equals c. Okay, my suggestion, because you are going to be substituting these numbers that you pick in a minute back to f prime, is that you pick numbers that work well with f prime. So our f prime derivative here looks like that. It's not too bad in this case, so but we want to choose numbers that are going to make our life easy. So between 0 and 6 is 1, so that is always nice. And to the left of 0 is -1, okay? And then to the right of 6, let's choose maybe 7. One thing to mention, it hasn't come up here, but I'll mention it anyway. I picked these numbers mostly because of their usefulness and simplicity in calculating f prime at those numbers. You'll see that in a minute. But it is also very important that you choose numbers that are in the domain of f prime, right? So if somehow the domain of f prime stopped at like -0.5, then I should not choose -1, right? If the domain doesn't include -1, I literally cannot substitute in -1. So that's a small technical point, but it's important, even though it's not coming up for this particular example. Okay, and then what do I do here? So I'm just going to, off on the side, calculate f prime of -1. At -1, I'm just looking for the sign SIGN. So I notice that this is 4x squared. That's going to be positive. If I put in -1 here for x, I get -1 minus 6. That's -7 times the positive number remains negative. Okay, I'm not going to write down the numerical value. We don't care about that. We only care that it's negative there. Okay, and then I do this again with f prime of the next number, which is 1. Once again, this thing up here is positive. When I put in 1 there, I subtract 6. I still get a negative number, -5. So this is also negative. So put a negative there. And then last one, f prime of 7. When I put a 7 there, still positive, but now 7 minus 6, that's positive. So that is overall positive. So I get a positive sign here. Great. And now we get to step back and use one of these 3 sign diagrams, if you will, to classify the critical number. You can see that this part of the diagram, the critical number 0, looks like the one down here. In other words, the function is decreasing before 0, derivative is negative, and it's also decreasing after 0 up to 6. Okay, so as we cross 0, we were decreasing before, and then at 0 we have a stationary point, the derivative is 0, and then we're decreasing again. So that means that 0 is not a local extremum, right? Wherever the graph looks like, right? It might be up here, I don't know, in the y-axis, it might be down here, I don't know. But I'll just sketch it like this. We were decreasing, and then we're decreasing again. So this does not look like a local extremum for the graph. So no local extremum at x equals 0. Now let's look at the other half of this sign chart. So let's look over here. So what about around 6? Well, right before we cross 6, the derivative is negative. Function is decreasing. Right after we cross 6, the derivative is positive. Function is increasing. So the function is doing something like this, and then like this, right? That does look like a local minimum to me, and that is literally what's going on over here in this second conclusion, right? Derivative goes from negative to positive as we cross C, local minimum. So our conclusion is that x equals 0 is not a local extremum, and x equals 6 is a local minimum. All right, so that's a really quick overview of using the first derivative test to determine whether there are local extrema, and if they are, where they are, and what type they are, like local maxima or local minima. Last thing I'll mention for this, just to bring things back to stuff that we had talked about earlier in the video, be careful when you are substituting in these values into your derivative, right? You again want to pick ones that are in the domain, and also computationally you want to pick ones that are easy to calculate with. 1 if it's possible, -1, things like that. Small numbers work very well. Okay, so that was it for this video, and I'll see you in the next one.